Dear students, welcome to another lecture of control systems. In this lecture, we will be discussing about the signal flow graph and Masson's gain formula. So this lecture will cover the introduction to the signal flow graph and rules to draw signal flow graph, and then we will also see the Masson's gain formula, right? So what is a signal flow graph? Uh, like in the block diagram representation, we understood the concept that how we can represent a given system through block diagram. So block diagram is a kind of pictorial representation of a control system, right? And through that block diagram representation, we can easily determine the transfer function of the given system. Similarly, we have the signal flow graph, which further, is used to, simplify a given system through a pictorial representation, and we can easily determine the overall transfer function, which is also known as transmittance in case of signal flow graph, conveniently, right? So a signal flow graph, we can say, is a kind of a pictorial representation of the given control systems, in which we generally do not have the summing points or takeoff points as we have in the block diagram representation. Instead, we have some other components which we would be discussing in this lecture. So signal flow graph basically is used to solve a given system pictorially in the convenient manner. Okay, so for example, if we have the block diagram representation of some complicated systems, so it becomes very difficult for us to reduce the block diagram and to get the overall transfer function of that particular system. So it is difficult, tedious, and time consuming. So in place of that, we have signal flow graph, which is an alternate approach to the block diagram representation. Signal flow graph is, uh, much convenient approach than a block diagram reduction technique. It is again a graphical representation of the relationships between the system variables, right? Signal flow graph does not require any reduction because there is a graph gain formula which directly gives the transfer function. So we don't have to reduce, like in block diagram reduction, we need to reduce the block diagram through the block diagram reduction technique. We have certain rules for that. However, in case of signal flow graph, we do not have any such kind of reduction. Okay, because we have a straightaway formula to determine the overall transfer function of the given system, which is represented through a signal flow graph. And that formula is known as Masson's gain formula. So we will be discussing that in the last slide of this lecture. So as you can see, this is a diagram wherein we have a block, and this block has some gain, which is, the gain of this block is shown here, right? So this is A, okay? So in this particular representation, as you can see, we have a system with gain A, and this has some input X1 and there's some output X2. So in signal flow graph, we can represent the same block representation with a graphical representation, which will have a line which represents the flow of the signal, right? Like in this, you can see that the signal is from X1 through A to X2, right? So it is from x1 to x2, and this A is now, no, it is represented on the line, and this here is known as transmittance. So this, okay, so this is how we represent. So we replace the block diagram representation with a signal flow graph by following certain, rules. There are very minimum rules for that, and they are very convenient rules as compared to the block diagram reduction technique rules. Now, there are certain properties of signal flow graph. Likewise, the first is we can obtain signal flow graph from the block diagram of a system, as we have simply seen in the previous slide that we have a block and we have some input to this block, which is x1, and there is certain output to the block, which is x2, and this block has certain gain A. So we can simply represent this block with a single signal flow line, which will have this A, which is now in this case known as transmittance, and this is x1 and this is x2, right? So this is how we can represent. Similarly, we can simply replace a block diagram representation of a system with its equivalent signal flow graph representation. Signal flow graphs can also be obtained through the equations. Like in this case, we can write this equation as x2 is equal to a x1, right? So x2 in this case is the output, that is the response, x1 is the input, and this is the gain, right? So we can reach to this, representation from this equation. Okay, and this equation must be in the algebraic form as it is, and it is applicable for the linear systems, right? So signal flow graph is applicable to the linear systems. Okay, so we can understand these characteristics by simply drawing a signal flow graph of this particular equation. So let us try to understand these characteristics. Signal flow graph can be obtained from the block diagram. So we can represent this equation as a block diagram. So we have x1, which is the output, right? This is the output. Okay, so now let us draw it here. So we will simply draw it like this. So this is x1. So a part of x1 is being multiplied with b, and it is going here, for example, and it is being added. So that means we have a summing point here, right? So it is being added with a signal which is x naught and multiplied with some gain a. So these two are added here, and the output now here, the output is ax naught plus bx1, which is equal to x1. So that means it is, okay, so it has a unity gain, means this path will have unity gain. So this is the block diagram representation of this equation, right? So we can easily get the signal flow graph of this particular equation, right? We can get the signal flow graph either from this equation or from this block diagram, right? So for example, if we have to get the signal flow graph from equation, we simply will have a node. This is x naught, which is multiplied with some gain a, and then we will be having, we have here x1. X1 is multiplied with some gain b, and this is the signal flow graph of this particular block diagram. So we can either obtain signal flow graph of a system from its block diagram, or we can also obtain the signal flow graph of the given system from the mathematical equations, which are algebraic equations of that particular system, right? So this is how we can easily obtain the signal flow graph. Now, what are the various components of signal flow graphs? Like in case of block diagram representation, we have several components of block diagram, like we have summing point, takeoff point, branches, block. Okay, But in signal flow graph, we have only two components. The first one is node, which is actually it actually represents a system variable which is equal to the sum of all incoming signals at that node, right? And then we have the outgoing signals do not affect the variable at the node, right? So these are the characteristics of node. What is a node? Node is a point in signal flow graph where some signals are, being added, and which will have some signals are going out of that particular node, right? So it may be a point like this, which will be having certain signals coming to this, and some signals are leaving this particular node, right? Then the second component of signal flow graph is branch. So branch is basically, that component of signal flow graph where the signal travels along it. Okay. So the signal travels from one node to another node in the direction which is indicated by the arrow. And then each branch will have certain gain, which we generally call as transmittance in case of signal flow graph. Signal passing through a branch gets multiplied by its gain. Okay, means if you want to get the response, then it is actually equal to the gain multiplied with the input, right? Okay, so let us see what is this. So for example, if we have some input to the system, okay, so let us say we have certain input, which is, let us say, x1, and the output is x2, and the gain of this is a. So this can be represented by, this signal flow graph. Okay, so a is here, x naught and x2. So these two are the nodes, right? And this is a branch, and this branch has a gain. This is the gain of the branch, and the signal passing through a branch gets multiplied by its gain. So the signal is represented with an arrow. Okay, it is represented with an arrow, and the signal passing, this signal is passing through this, so it is multiplied with a to give you the response x2, right? So there are two main components, or only two components, which are the major components of signal flow graph. The one is node and the another one is branch. Then there are certain rules to draw the signal flow graph. What are those rules? So first of all, the signal travels along a branch in the direction of an arrow. Okay. So like we will take the previous example, x1, and then you have x2. So these two are the nodes, right? And it has a gain here, which is the transmittance. This is the transmittance or gain, right? Okay, so this is an arrow. The signal travels along a branch in the direction of arrow. So the signal is traveling from x1 to x2, right? Okay, so the second rule is the input signal is multiplied by the transmittance to obtain the output signal. Okay, so this response x2 is actually equal to the product of transmittance of the path or the branch and the signal that is coming to that branch, right? So third is input signal at a node is sum of all the signals entering at that node. So there may be a possibility that you have some signals coming like this. Okay, so if it is a node, so if it is, let us say, x1 and x2 and x3, so x3 is actually equal to x1 plus x2. So at a node, all the signals are, okay, means those signals which are entering at that node are added. They are added. Then a node transmits signal in all the branches leaving that node. Okay, so this is the branch which is leaving it node. It will transmit the signal to other branches. So the terminology that is used in signal flow graph is, the first is input node. Okay, so it is that node which only has the outgoing branches, as you can see in the diagram, which is shown adjacent to this point. we have, this X1. So this is actually the input node. Then we have intermediate node, or which is also known as mixed node. So the mixed node will have both type of branches, the incoming branches as well as the outgoing branches. So as you can see here, this X2, this is the intermediate nodes. This is the intermediate node, right? Or we can also call it as a mixed node. Then we have the output node, which only will have the incoming branches, right? Or it may also have, if this is not the case, then we can, we can extend this to get one more node with the gain 1, right? So that would become the output node in this case. Okay. Then the path. So path is basically the, it is the traversal of all the connected branches in the direction of arrows, such that no node is traversed more than once. Okay. So like this is the path. So this is the path, x1 to x2, then from x2 to x3. Okay. Then forward path is the path from input node to the output node. So as you can see, this is the forward path, this one. Then loop, a loop up. This is the path which originates and terminates at the same node. Okay. So as you can see here, so this is a loop which has originated from x2 and terminating at x2 through x3. The non-touching loops which will not have any common node, and the path gain, the product of gains encountered in the traversing path or loop. So the path gain here is like this one. The forward path gain is A into B, but you have this one also. So it would be AB divided by 1 minus BC, right? These are the terms which will be used in the signal flow graph. Now let us understand the signal flow graph through this example. We have this block diagram. We can easily get the signal flow graph from this block diagram. So the first thing that we need to do is we need to identify the nodes and the branches. Okay, so all the takeoff points and the summing points or the feedback points, they are generally represented through nodes, and the blocks are represented through transmittance with an arrow, right? Okay, so we will be having this R here. So this is, let us say, R, which is the input node. Okay, so now this summing point is again a node. Okay, so this is also a node. Now we have this takeoff point. This is takeoff point. Now, this takeoff point can also be a node, but then we need to identify whether it will be a separate node or it will be, added with this summing point. So now let us see what is the output at this particular point. The output at this point is R minus H1C. So this is the output. Now, what is the output at this point? It is R minus H1C. So we have the same output throughout this particular point. So in this case, this node will not be taken as a separate node. It will be taken as a common node. So these two will be common, right? So it is, for example, some node, let us say X1, for example. So it is 1. So from this R to X1, we have a unity gain 1, right? Then we move further. So we see that we have G1. So G1 will be represented as the transmittance just written above the arrow. And then we have this. Now this is a summing point which will be which will be represented with a node, right? Then again we have this one which is again which can be represented as a node. But let us see what is the output at this particular point. At this point, the output is G1 plus G2 and multiplied by this R plus R, sorry. So it is G1 plus G2 into R minus H1C, right? So now what is the output here at this point? It is again same output. This output is again here, right? So these two will be having same output. So can be considered as the same node, right? So it is same node. For example, this node is x2, and then we have see the output, and the gain here is from this point to this point, it is 1. So we will take it as 1, right? Now we can see that this is a common node which is represented by this one. This is a common node which is represented by this one, right? Now we can see that we have a takeoff point here, right? So we will take a point. We'll take a point, and the transmittance of this point is, sorry, we'll take a branch, and the transmittance of this branch is G2, and it is, terminating here. Okay. Similarly, we can see we have a feedback point here. Okay, this is the feedback point, right? This is the feedback point. So this feedback point is taken from this side, right? So we will take a feedback point from here, and the transmittance of this feedback point is H1. So it is H1, and now it will go where it is being terminating. It is terminating at this point. So this point. So it will go like this. Now, because it is a negative feedback, and we don't have any provision to write plus or minus at the nodes. So what we will do is we'll mention negative with the gain of the feedback path. Now this is the signal flow graph of the given block diagram. And the best part is that you don't need to apply the block diagram reduction rules on the signal flow graph, right? To get the overall transmittance of this signal flow graph, we have another concept which we call as Masson's gain formula. So the purpose of Masson's gain formula is to have the overall transmittance, or we can say to have the overall gain or overall transfer function of the given system, which is represented by a signal flow graph. So the formula which is given is written here. The overall transfer function or the transmittance of the given system represented through signal flow graph is summation k is equal to 1 to n pk delta k by delta. Now where tf is the overall transfer function of the system, pk is the path gain of kth forward path. So we need to identify how many forward paths are there, right? So as in this case, if you see, we have this forward path, then we have this forward path. There are two forward paths, right? Okay. So uh, so the gain of kth forward path. So there are two, there may be n forward paths. So we may be having n gains, means gain of, we will be having gain of each forward path. Then number of forward path, n is number of forward path. Delta, it is the determinant of the graph basically, and it is generally given by 1 minus sum of the individual loop gain. So we need to determine how many individual loops are there in the given signal flow graph. We will add the gain of all such loops, right? Then plus sum of gain product of all the combination of two non-touching loops. The next thing that we will do is that we will try to identify the number of non-touching loops, two non-touching loops in the given signal flow graph, and then we will multiply. We will have their gains, gain of each loop, and we will add the gain of each such loop which are not touching each other. Non-touching loops are those loops which do not have any common node, right? Then minus sum of gain product all combinations of three non-touching loops. It means that After identifying two non-touching loops in the signal flow graph, then we will hunt for or search for three non-touching loops in the signal flow graph. We will write down their gain of each loop, then we will add those gains, right? And so on. We will keep on doing this thing. Then we will be, adding the gain product of possible four non-touching loops, then possible five non-touching loop, then possible six non-touching, and in this way we will keep on going, right? Now this is what delta is. Now what is delta k? Delta k is the value of delta for the part of graph not touching the kth forward path. That is, it is equal to the value of delta for a reduced graph with nodes and branches in the kth forward path removed. Now what does it mean? For example, you have two forward paths, right? So there would be two delta, delta 1 and delta 2. So we need to see that loop which is not touching this particular path. So delta 1 is equal to 1 minus the gain of that loop which is not touching first forward path. Similarly, delta 2 will be 1 minus gain of that loop which is not touching second forward path. So in this way, we will have to identify this. And once we identify all such things which are mentioned in this formula, we will write down here, and then we will find out the overall transfer function using this particular formula, which is Masson's gain formula. This formula is very important formula as far as the concept of determining overall transfer function of a given system is concerned, right? So in this lecture, we have understood what is signal flow graph, what are the characteristics of signal flow graph, how can we draw a signal flow graph. There are certain rules to that. We have also seen the terminology that is used in signal flow graph, and we have also seen that how we can obtain a signal flow graph from block diagram representation. And then eventually we have understood what is a Masson's gain formula. And in the next lecture, we will be doing certain numerical problems related to signal flow graph, and we will apply the concept of Masson's gain formula to determine overall transfer function of the given system represented through a signal flow graph. So now this is it for today's lecture, and thank you so much.